Okay, today is February 22nd, 2022. It's Tuesday, Physics 38 at LA Harbor. And we are calculating the electric field due to a annular distribution of electric charges. Okay, so here is the drawing of annular distribution of electric charges. And I want to know the electric field at any point along an axis that passes through the center of the ring, perpendicular to its plane. So how do we do that? You know, we want to calculate this electric field at this point x along this axis. So what do? We look at the contribution of each infinitesimal charge on the ring. This charge, the contribution of this infinitesimal charge here, this lower place, should be minus r, okay? Minus r. Here should be minus r as well. Should be this vector in this direction that makes an angle phi with the x-axis. If we take another point on the other side of the ring at the top, y, right? Don't forget here is minus r along the z-axis. Here is minus r along the y-axis. We get another vector that's going to have the same angle phi, because this length here and this length here are the same as this length here and this length here. The angle phi here is going to be the same as this one. If we integrate throughout the whole ring, what we are going to get? We are going to get an electric field distribution that's going to an infinitesimal electric field contribution that's going to span a cone in space around the x-axis. The result is going to be an electric field that's going to point only along the x direction, because the components along the y and z axis are going to cancel out. Okay, like I mentioned before, here you go. Suppose here my arm right now is my x-axis, and I want to determine the electric field here at this point, at my joint. Okay, and then we have this vector position that goes from one infinitesimal charge in the ring until this point. The vector position goes from here to here, and the ring is right here at the tip of my finger, a piece of the ring. This vector position spans a cone in the three-dimensional space. And the distance for here we have an infinitesimal charge contribution, here we have another infinitesimal charge contribution, and so on. So each infinitesimal charge contribution in this ring has the same distance to the point where I'm trying to calculate, right? So what do we have to do? Okay, what we have to do is the following. All we have to do is to find out what is the contribution of the electric field contribution of each infinitesimal electric charge, and multiply by the cosine of phi, which is going to be the x component of this electric field contribution. Okay? That's what we have to do. The distance here is always going to be the same throughout the ring. This distance r we can calculate, and it's going to be like that. Here you go. The field of a ring. The field of a ring of radius r, right? The field at a point r, at a point along the x-axis at a distance x, a distance at position or distance at a position x the center of the ring is located at the origin of the XYZ of the XYZ axis. So here you go. The infinitesimal electric field contribution of each. Let's see. We do know that the net electric field is going to be given just by the x component of the electric field, just by looking at that drawing. Okay. Okay, making a qualitative analysis of the electric field distribution using the drawing, using a drawing, comma, we determine that the net field, will have only a next component, or we can also state that the electric field contribution, also from the drawing, right? Also from the drawing, we can also state that the field contribution of each infinitesimal charge, electric charge dq is, here we go, infinitesimal electric field contribution is going to be that of a point charge. K dq r square. Okay, the right notation should be r prime square. Okay, because the distance from the charge to the point where we are calculating the field is cosine of phi. Oh, this one here. Yeah, phi, like that. Let's go back to the drawing. Here you go. That's the angle phi. This angle phi here is equal to this angle right in here. So we can state that x divided by r is cosine of phi. Okay? You see how important it is to do those drawings? So x divided by r prime, right? X divided by r prime is equal to cosine of phi. Okay, oops. X divided, I'll put it here as r prime to make it consistent with the notation that we have. Like that. R prime. R prime. Prime. I gotta fix that too. Should be a negative big R, right? Negative big R. have the same one here, negative big R, negative big R. I know I got those mistakes. Go. Yeah. Okay, here go the other one in the other contribution here, right? In the along the z axis, we have the same angle phi here and here, resulting. So this drawing here should go before the other one. Right there. Okay. Oh, here you go. All right, here we go. Bring point X along the x-axis, contribution of the infinitesimal charge in the negative R along the y-axis, contribution of the other charge in the positive y-axis along the z-axis, and here would be the net field. If I want to show in some detail the cone, I can put this guy here as well. Interesting. Okay. And then we have this cone minus R, oops, minus R here, minus R there. Okay, so I can put also the drawing here of the infinitesimal charge, right? On those points along the z-axis, right in here. Because this ring is uniformly charged, the amount of charge at those positions is going to be the same. Okay, and here we go. Gonna do this other one right here. Send to the back. DQ. Okay, if I want to, I'm not gonna do that because it's too much work. Okay, so let's go back to our drawing, to our calculations. Here you go. That's the calculation right in here. I can go ahead and simplify the thing, making r prime cube x. My r prime can be written down in terms of the known parameters. My r prime is going to be what? It's going to be that square root that you're already aware. R is square plus x square. And what else? I have to cube this guy here. Remember, it's square root, right? But first, let's put the cube there because we have that cube thing. Not this one, it's this one that, yeah, that's the one. Well, not that I'm here. Yeah, like that. So I put my parentheses right in here. There you go. Okay. We have the x upstairs, the x here is also downstairs, and we have to integrate over q. Don't forget, x here doesn't change, okay? Remember, I'm integrating through the whole ring. The position x remains the same no matter what. What changes is the position along the ring. But the distance from the ring, from the infinitesimal charge on the ring doesn't change when we integrate. Okay, so let me show you what happens. Here we go. If I want to know the net electric field, what we have to do, we have to integrate over this whole guy. And the the domain of integration is the ring, where the ring is located. Here you go. Now let's go ahead and take everything inside, everything that's constant, we're going to take out from inside the integral. Remember I told you the x doesn't change, right? The x and the k also doesn't change, is a constant. Because the r is also a constant, this whole denominator can go outside as well of the integral. They are all constants whenever you integrate over with respect to the ring. And then we end up with a simple integral. Remember I told you this is a one-dimensional problem? It is a one-dimensional problem if we use the polar coordinate system, but we don't need to get into that. All we have to do is to take a look at this integral here. If we integrate an infinitesimal charge throughout the whole ring, we are going to get the net charge of the ring. Okay, and I have to, here you go, calculate the field, here you go, calculate the field of a ring of radius r and net charge and uniform the field of a ring of radius r and uniform charge distribution, comma, uniform charge distribution and net charge q, okay, at a point. Okay, so solution. So treat that as though is a problem. And now we have the net electric field right in here. I can here write that down. Let's see if it's right. That's the net electric field here. And let's not forget, this is an electric field along the x-axis only. And I'm going to do even do the following. Here you go. This guy here, I'm going to put, I'm going to emphasize the x component of the electric field. I'm going to emphasize that this guy is the x component of the electric field. Okay. And I can here write the net field vector as this x component field in the x hat direction. I'm gonna put it BQ right here. Don't forget the square root is raised to the third power. Let's see how it's in my notes. Here you go. Electric field. Yeah. Okay, KQX. All right, I put in a different notation. I put power 3 halves. KQX, R square plus X square. I can change that too, if you prefer this notation, right? We put a parenthesis there inside the square root, and then we eliminate the square root by writing the power of 3 halves there. And now I don't need the square root anymore, not even the cube outside. KQX, divide by that. Okay, we're gonna do that approximation again. For x much greater than r, comma, we can neglect the r square in the denominator and get the Coulomb's law, the point charge expression for the E field. Okay, it's like that. Here you go. We neglect that, and don't forget always to put an approximation here. Neglect this term. We get the x squared raised to the power 3 halves. All right. Here is an equality because this term is equal to this term, right? But not this term. This term is not equal to this term, so you should be using this approximation. Okay, so you can go to the next step here. You get the cube, x to the cube. Okay, we cancel x with x cube, and then we get the field of a point charge. Here you go, see that? The approximation sign. We have an approximation sign here, but not here, right? Because this guy is equal to this guy. Because this guy is equal to this guy. Okay, so that's what we have for this derivation. And what's going to be the next one? Let's see. Okay, we did this one, right? Yep, we did this one. Okay, now we're going to do a two-dimensional charge distribution. What we did here was a one-dimensional charge distribution because this charge distribution can be in the polar coordinate system becomes a one-dimensional charge distribution. That's why I call that 1D. Now, what we're going to do next, we're going to get the electric field of a disk that has a uniform charge distribution. Okay, here we go. Let's get minus here. Gotta fix all the stuff. Here you go. Let me see if I can hunt for everybody. Replace with minus R. hopefully, fine. Yep, place of 29. Good. Hopefully I got it right. Just like before, we draw the disc. Now, here you go. Let me write that down here for you. Repeat the above. Here you go. Calculate the E field. The E field of a disk of radius r, uniform charge distribution, and net charge q at a point on the x-axis at position x. The center of the disk is located at the origin of XYZ axis. Okay? Making a qualitative analysis of the electric field distribution using a drawing, we determine that the net field, again, just like before. Okay? The net field, again, has only an x component, just like before. Okay? But before we do that, what we're going to do, we're going to get an infinitesimal charge distribution that's going to be a ring. So this disk is made up of infinitesimal charge distributions that is a ring. Here you go. This ring is an infinitesimal charge distribution, and then there are several rings there, okay? See that? So this ring contributes an electric field just like we got before, right? There's a cone. It describes a cone in space. And then you have other rings. What's that? Strange. Yeah, I don't know what that drawing is. Okay. And then you have several other rings that does the same. Because the infinitesimal charge is a ring, we are going to end up having an electric field that's just along the x direction as well. Okay, and we are justified to state that again. Let's see here. We're going to have a contribution, an infinitesimal contribution of the electric field that's going to be given by an angle, by a term here that's multiplied by cosine of phi. With one important difference. This phi is going to change as I integrate from the center of the ring to the center of the disk to the outside of the disk. Okay? This angle phi is going to change as we span this vector here from the center, right? The phi angle here in this case is going to be 0. And as I integrate through different rings along the disk, this phi angle is going to change. Make sense? Right? So here you go. We have our dq here, and now this guy is going to be is going to change as we do our integration. So what we have to do, let's see. Oh, I'm going to do something else, just like before. Cosine of phi is going to be x divided by r prime, right? Just like the other one. Let's go back to the drawing here. Here's the x, and this is the r prime from the center to the position of the ring. Okay? Let me see if I can do another drawing here for you to understand. Here you go. That's one infinitesimal ring. The next infinitesimal ring is going to be this one here. Okay. And I'm going to, I can even decrease the size of the infinitesimal ring. Here you go. That's the other infinitesimal ring with a different r prime. Notice that now the r prime is changing as we integrate throughout the whole disk. Okay. This guy is gonna go here. Oops. It's gonna get that. Okay. Like that. How do we calculate that mathematically? Well, we go ahead and recognize that this infinitesimal ring, when I cut it and extend it, becomes rectangle, a rectangle of side dr prime and length 2 pi r prime. Okay, 2 pi r prime and thickness dr prime. That hard, but before we go that, we have to rewrite our dq here. Okay, let's rewrite our dq. Let's see here. R prime. Wait a minute. Oh, wait a minute. There's something wrong here. Yeah, the notation. It's a matter of the notation, okay? A matter of the notation. I'm gonna call this not r, not lowercase r prime. I'm gonna call that. Yeah, we gotta have always to be careful about notations. But the notation can make or break the solution of your problem. Yeah, I didn't have it here. Okay, so here you go. There is the radius r, and then there is the radius of the ring r prime. The radius r is the radius of the disk. The radius r prime is the radius of the ring, of the infinitesimal ring. Okay, so let me just, and this r prime is gonna change. So that's a better notation. Remember, okay, when you're solving problems, it's very important to get a good notation and keep track of that. Here you go. I'm gonna put the r prime here, r prime here as well, big R prime, big R prime. Here you go, R prime. Ooh, oh gosh, I'd rather get this thing here, not symbol, but ideal, ideal. Here you go, R prime. Let's change everything. Let's make sure you change it everything. R prime here, R prime here. The R, big R is a constant, but R prime in our problem is a variable. Go. R prime, go. Okay, that's something else. So let's concentrate on that. Oh, let's not forget that we have our little R prime here as well. We make the distinction of the lowercase r and the uppercase, the lowercase r prime and the lowercase r. What's the distinction between them? The lowercase r prime means the distance from the charge to the point. The lowercase r is the distance of the origin to the point where you're calculating, okay? That's the distinction between those two coordinates. don't forget, you gotta come up with a good notation every time you try to solve a problem. Oh, one more. Yeah, we got it. Am I forgetting anything? Okay, so here you go. Almost everything that we did for the circle, for the ring, applies right in here. But the only difference is the big R, right? Instead of big R constant, we're going to use big R prime as a variable, which is the position of each ring during the integration of the. Do you need to do anything? Yeah, I'm gonna need this one here. I need this other. EX, but don't forget that's gonna be R prime. That's the one that's changing. And now we cannot take this one outside the integral. We cannot take this one outside the integral. We cannot take this one outside the integral because R prime now is changing as we integrate throughout the ring, right? Throughout the disk. So here you go. Here's the disk. Here's the disk. So what we're going to do, we're going to integrate over this ring at the edge, and then another ring just inside, another ring. We're going to integrate from the radius r, or sorry, we're going to integrate from the radius 0 to the radius big R. Okay? This distance to this tip of my finger is what I call capital R prime. Okay, and I'm going to sum the contributions of the electric field of every small ring inside this disk. So now this thing doesn't apply anymore because it's not a constant anymore. So this thing here, I want to change the notation to, let's see, instead I'm going to use the following. I'm going to get this guy, yeah, this guy right in here. I prefer this notation of 3/2. Okay, I'm gonna put right in here 3/2. But don't forget to put R prime. And now I can go ahead and yep. We can't, here you go. We're going to like that. K is a constant, X is a constant. And now we are no longer integrating the ring, we are integrating on the circle. Okay, and next step, circle, circle. What's the next step? This one doesn't apply anymore. Okay, the next step is to try to change this guy right here in terms of the integrating variable r prime. That's the next step. Okay, but before we do that, what we're going to do, we're going to write dq in terms of the surface charge density. So what does it mean? It means that dq divided by dA, infinitesimal charge q divided by infinitesimal area A, dA, is going to be given by a charge density, uniform charge density. Don't forget this one is uniform charge density, right? Did I write that down here? Calculate a uniform charge distribution. If it's non-uniform, the problem is more difficult mathematically. Having written that this way, now we can here write my dq in terms of sigma and dA. Sigma and dA. And substitute right in here. Let's do it. writing here. Circle. Going back to our drawing, we can write my dA. And by the way, I'm going to write not dA. I'm going to write down dA prime to remain, you know, consistent with our notation. Remember, is the area of the ring, right? Of the ring, no, it's the area of the disk. I'm going to write that down as dA prime, just to anything that's inside the charge distribution, we put a prime in there. That's the consistency. Okay, let's go back to our drawing. Here you go. The area dA prime is going to be the area of this rectangle that I told you, right? How do I get this rectangle? Okay, I got this ring here, that's my infinitesimal charge. I cut it in half and I stretch it. Okay? It can be approximated to a rectangle because we are making the r prime going very small, to go very small, going to 0. So the area dA prime is going to be 2 pi r prime dr prime. Going back here you go. dA prime 2 pi r prime dr prime. Okay, like that. Circle. And the sigma is going to be net charge divided by net area. Is uniform charge density. Net charge is big Q pi r. Now is going to be the regular r because it's the radius of the disk. It's not r prime, it's r. The area of the disk is pi r squared. And we are going to get rid of everything that's constant. Take out from the integral everything that's constant. Take out from the inside of the integral. Let's see, can we, yeah, we can cancel the pi with the pi. And all that stuff here goes outside. Like that. I should have left this r there, the 2 there inside, but that's okay. And now we have to struggle with this integral. Now we changed the integrating variable from dq to r prime, from dq to dA prime, and from dA prime to r prime, right? So when we change the integrating variable, okay, we should put here the area. When I change it to r prime, so we're going to integrate from 0 to big R. Integrated from 0, oops, to big R. Integrating it from 0 to big R. This integral, you know how to solve, right? You know how to solve this integral. We have a 3/2 here, negative. How do we get a negative 3/2? We get a negative 3/2 by differentiating a negative 1/2. Let's do that together. Here you go. I'm going to get here. I'm going to put negative 1/2 here. Negative 1/2. When I differentiate this term, what do I get? I am going to get a minus half that I can cancel out with minus 2 upstairs, right? This guy becomes minus 3/2, just like I have here. And then what else? We have to differentiate the inside of this term, which is going to become 2r prime, dr prime, right? r prime, d r prime. The 2 that comes from this differentiation, we divide by 2 to get the right integrand. And so that's how we get this term here when you differentiate with respect to r prime becomes this one right in here. Okay? Let's do it. Here you go. Let's differentiate that by head, right? Do that by head. Minus half. I'm going to do it. No, I'm not going to do it by head. I'm just going to do on the paper here for you. On the paper. It's not the paper, right? Differential. D. Here you go. Dr prime. Dr prime. Okay. Dr prime. What's going to be? Oops. The 2 cancel with 2 becomes minus. Okay. And now we are left with this one here. Here we go. What we get? Minus half. I'm just proving to you that what you see here is going to end up becoming that, okay? Minus half. When we differentiate that, this guy becomes minus 3 halves. I don't need to have my differential there anymore, right? So here we go. Now we have to differentiate the inside of this thing. Is going to become 2r prime, right? This 2 cancel with this 2. The negative cancel with the negative. Okay, here we go. Negative cancels with the negative. And look what we get. Yeah, I proved to you that this guy here is indeed the integral of this guy here. Okay, of this guy here. Now let's apply the limits. R prime, big R prime, from 0 to big R. I think I should put a good idea to put a bar here. Use the proper notation. Oops. Bracket separator. This one. Right bracket only. Let's see. Right ceiling bracket only. Here you go. That's the one. Okay. Not exactly what I want, but that's okay. This guy is going to cancel with this guy. We're going to get only the negative here. Very important that you perform those derivations as well. Okay. Now we apply the limits. Okay, so here go. r, that's the first term, right? And I'm gonna put the 0 right in here. 0. And now I no longer need those limits anymore. Let's see what else can we get. What else can we get with this? So what we end up here is going to be 1. 1. There you go. And this x squared is raised to the minus half power. What end up being? It end up being 1 divided by x. That's what we get when we raise x squared to the minus half power. There's one more step that we can take. Notice that this term here is less than this term, right? So you can rewrite that just by switching the signs. Here you go. And canceling the negative on the outside. Like that. So that's the electric field of the disk. Can I do anything else here to simplify? Doesn't look like. I'll put this kx there upstairs. Okay, let's do another step. What about r much greater than x? Every time that we get r much greater than x, you're supposed, for something like that, you're supposed to get the r squared term. In this case, the r squared term is going to be our x squared term. Let's see. Did I do something wrong here? No, doesn't look like. Let me see. Let's compare with my notes, and hopefully I didn't make any mistakes. That's going to be, yeah, that's the linear charge distribution. This one here should be what? Yeah, that's the disk. Disk. Let's compare my notes with what I got there, and I did on the fly, right? 2kqxr squared. 2kqxr squared. Good. 1 over x. Yeah, r squared. No problem, right? Yeah. Okay, now let's do the r much greater than. No, it's not r much greater. It's all the way around. R much less than x. Much less than x. Okay, so here you go. If we do the lazy way, okay, we get the trivial solution. Okay, what's the lazy way? The lazy way is by making r equal to 0. See, if we make this guy 0 here, right? So you gotta be careful about those approximations. You get square root of x squared becomes like that, and you get 0, you get the trivial solution. So this approximation doesn't work. This lazy approximation doesn't work. We gotta do the procedure that's more rigorous. Okay? Okay. Because we are getting the trivial solution, we must use the binomial approximation instead. Okay, the lazy way is just like the zero order approximation. So let's use the binomial approximation for this term here. We're gonna use the binomial approximation for this term here. Here you go. That's what you gotta do. Binomial approximation, you gotta come up with first with the equal sign, then we worry about the we gotta put what? We gotta put the x squared in evidence and r squared over x squared, right? Plus 1, like that. Oh, don't forget the square root. Yeah, I gotta put the square root too. Square root here. Okay, square root. Here you go. Okay. What you have right in here is exactly what you have right in here. And now that I put it in a different format, well, there's one more thing that I gotta do. I gotta take this x squared outside the square root, and it becomes, okay? I'm going to swap the one with the r squared over x squared, like that. And now we can start working on the binomial approximation. Now it's easier to do the binomial approximation when we put those guys in this format. Okay, let's do one more step. I'm going to separate the 1 divided by x by the 1 divided by the square root. Okay, I'm going to do like that. Okay, here we go. Separate it as two fractions. Right, so here we go. The approximation that we're going to deal with is this one here. Okay, so I still have a equal here. Okay, the approximation is gonna come now. Oops. Let's see if I have space here to do that. Binomial approximation states that it's gonna be like 1 plus minus half, which is the power of this guy here, minus half r squared divided, oh, I don't want the r x squared there. I want the x squared here, divided by x squared. That's how, like that. Oh, almost there for a break. Hang in there. Let me finish this approximation here. And here we go. Can I do more? Okay, I can. The only thing I need to do here is simplify that. Right? Oh yeah. Here you go, like that, half. Here you go. That's the approximation. Let's see if we get a better result now. Here you go. That's the one that we have to apply the approximation. Have to apply the approximation to this term right in here. And let's not forget to put the approximate sign. Okay. Let's not forget that what you have here is going to be equal what comes here. And here you go. We're going to have minus. I'm going to distribute the minus right in here. And, right, minus with minus is going to be plus. And look what we get. The 1 over x still cancels the 1 over x, but we end up with a non-zero term. So we no longer have the trivial solution. The x that we have here combined with the other x becomes r cubed. Okay. What else can we do? Oh yeah, there's more we can do. Let's see, one more. There is r square here, cancels out with the r square. Come on, man. Okay, this x cancel out with this x. The 2 cancel out with the 2. Okay. 2kq over x squared. You know. And now I can write my final solution, my final approximate solution as being 2kq over x squared. See the x squared here downstairs? It's just like the point chart. Okay. What do you say? Oh yeah, the 2 cancels out. Thank you. Yeah. Yeah, this 2 cancels out with this 2. Good. So it's 6:02 now. Let's take attendance. Excel. Today is the 22nd. Jimenez, Mario Acevedo Jimenez. Are you there, Mario? Nope. Toby? I saw Toby here. Okay, thank you. Harum? Musa? Genesis Bell? Jennifer Camarillo? No Jennifer Camarillo here. Robert Faust? Next is Pedro Flores. Lawrence Flores. Alexander Garcia. Sungham. Brian Ines. No Brian Ines here. Athena. Dylan Martinez. Rafael Mercado. Alexis Negret. Abraham Perez. No. Nicolas Pisano. No, what happened to Nicholas? He came last time, huh? Is Nicholas here? No? Okay, Ramon Quintana. Ali? Ali not here? Chaves? Kenny Villagomez? There. Patrick Villalvazov? No Patrick. And Nolan Williams. Okay, we have 16. Don't move yet. 2, 4, 6. Okay, good. So it is 6:05 right now. Let's get back at 6:20. Break till 6:20. Okay. I see you in 15 minutes. Okay. It's cold out there. Let's see. I'm gonna pause here. What's next? Here we go. We did this one here. Okay, let's just make a. Oh, yeah. Let's just make a summary here, right? Summary. You know, E field point charges. You got one point charges. A ring, a rod, and disk that we did so far. Calculate the E fields, but we calculate the E fields of those three only for some all those fours, right? Only for some points in the space, not the whole space, right? Calculating the electric field in the whole space is more difficult. It's more involved mathematically. We're just doing E fields, for instance, for the disk along the x-axis, right? That's what you're doing. The ring we did along the x-axis as well. And for the rod, we did only at the origin. If you are going to do anywhere in space, it's more complicated. You're gonna get you have to get, you are going to get a mathematical result that's more involved. Okay, just keep that in mind. What we're going to do now, oh, we're going to do one more thing. What we did this approximation here. Okay, we did an approximation for which x is much greater than r. Okay, when x is much greater than r, this disk here behaves just like a point charge because it has a net charge q. That's what we obtained mathematically, right? Kq over x squared, point charge. Every, you know, every object that is electrically charged, that has a non-zero electric charge, has this type of behavior. Very far away from the object, you are going to get a point charge behavior. Okay? But what happens if you get the x at a position that's very close to the disk? We can do that too. Here you go. What about, and we don't need the ring there anymore. Here you go. I'm gonna take out the ring here as well. What about we did for x much greater than r? What about r much greater than x? Oops. Hmm. Here you go. What about x much greater than? What about the opposite, right? What about x much less than r? What do you get for the electric field when the part on the point is very close to the surface of the disk? Okay, let's do that. You gotta apply again, you gotta apply the binomial approximation. Here you go. Right in here. Binomial approximation to this term, right? So let me get, here you go. I'm gonna write down the exact solution. That's the exact solution. Exact solution. Exact solution along the x-axis. That's the exact solution along the x-axis. And then I need you, what we're going to do, we're going to find an approximation for x much less than r. Okay? So if we get x much less than r, okay, for x, can we make x equal to 0? For x much, let's see if we can make, let us try the lazy way first. Let us try the lazy way first to determine if we get a good solution. Right? A non-trivial solution, right? A good non-trivial solution. Non-trivial solution for our electric field. And the lazy way means making, lazy way means what? Making x equal to 0. Sometimes this lazy way works, sometimes it doesn't. So the first thing that you have to do is to ensure that this x that outside the parentheses goes inside the parentheses. That's the first thing that you gotta do. Okay. When you do that, this term becomes 1, right? And what else? This term becomes 0, and this term also becomes 0. And look what we get. We get a non-trivial solution, right? Even more interesting. Oh, and by the way, here is going to be an approximation. And then, so you don't need to do more than that. Here you go. So I want you to look at that and look what's happening. What we're getting here is a 2 is a constant, K is a constant, Q is a constant, and R is also a constant. What you see here, you have an electric field that's not a function of X. You have what we mean a uniform electric field, very close by the disk. And by the way, that's what we ended up getting. We're going to see today in the lab. That's what we ended up getting in that lab that we did before for those two plates close to one another. You're going to see that what you have there, the data that you got, is for a uniform electric field as well. Okay? So keep that in mind, right? Oh, don't forget, we cannot always use the lazy way to solve an equation, to solve a problem, right? We cannot always use the lazy way to solve a problem, okay? If the lazy way results in a trivial solution, then you must apply the binomial solution, the binomial approximation to get your solution, to get your non-trivial solution. Every now and then, by using just the lazy way, we find a non-trivial solution. But sometimes we don't. When that happens, you use the binomial approximation. If you want to get another order term, we can do that too. We can do that too, okay? So here you go. I'm gonna do that just for the sake of seeing what happens, okay? What result do we get if we use the binomial approximation, right? Let's do that just for the sake of finding out what is the. Let's use binomial approximation instead. Here you go. I'm gonna get this guy right in here, copy and paste it. But now here, now we're gonna go the other way. Instead of putting the x square in evidence, we are going to put the r square in evidence. Let's see if we get. Here you go. When we put the r square in evidence, we get something like that. Here you go. We get a x square here. Oh, we get an x square here and an r square here, right? See, this one here comes from this term, and this term here comes from this other one. Okay? So I'm gonna commute those two terms so you know exactly what's happening. Just like before, we can take this r outside the square root. When we take the r outside the square root, the r square, when you take the r square outside the square root, the r square becomes r. And now we can start applying the binomial approximation. Instead of 1 over x here, we are going to have the 1 over r. The 1 here is just like this one here. This minus half term is just like the power that we have here. Okay, and what's come next is this term here. Is what I call my second order term. My first order term is 0. My second order term, because it's raised to the second power. Oh, wait a minute. Do I have it right? Yes, I have it right. Okay. That's the approximation that we get to the first order. And now let's substitute there in our exact solution. Here you go. It's going to be a little bit, messy. Here you go. Right in here. And let's not forget that what was an equality becomes an approximation. Okay, this x goes inside, Here you go. This x divided by x becomes 1. What else? Let's see, I'm going to make it so that what we end up getting if we use our second order approximation. Our second order approximation is in reality dependent on x cubed, right? I'm going to put here you go. Our second order approximation on this ratio here ends up being dependent on the, here you go. This negative becomes negative, yeah, and that this one here becomes positive. Here you go. Cube and cube. This negative sign disappear, right? And it's like that. Did I get it right? X over x is 1 minus x over r plus half x cubed r cubed. That's what we get when we go for the first order term, right? We have, here you go. We have the term, oops. We have the term that we got before. And then we have a first order term in x over r and a third order term in x over r. Zero order term in x over r, first order, third order. Did I do it right? Yeah, I did it right. Okay. You know, compare the solution is this solution here. Right? Let's put them side by side. Yeah. Okay. So what you have here is exactly this term. Okay. Let me see. Why do I have 2 in there? Yeah, that's right. Let me take a look. I'm suspecting these 2 here. X much greater than R. how much greater than x? Yeah, this 2 is supposed to be there. Okay. So what is okay for cases in which you are very close to a charged surface, a very close planar surface, doesn't have to be a disk, okay? Can be a square, can be whatever you want, provided you are very close to the surface, you can say that the electric field is going to be uniform, okay? If you want, a first order or a third order approximation, sometimes we need to do that, you may, this first order and third order approximation would apply for points that are a little bit further away from the charge distribution. Okay, so the experiment that you did last week, you're going to get an electric field that's uniform, and that's what I'm going to show to you today when we start plotting the graphs, okay? And we get 2kq over r squared, okay? So let's write that down. For points that are very close to the charge, to the planar charge distribution, we can express our field as okay. As we move further in, okay, we can say that in this case, let's see here. And for points that are very close to the, and what do I mean by very close to the planar charge distribution? Okay, what it means that x divided by r is less than 0.1. Okay, that's what I mean, less than 1/10. As x divided by r becomes larger than 0.1 and still less than 1, or something like that. Wait a minute. No, it's all the way around. 0.1 here, less than 1. Okay. We may use the other solution, the approximated solution, right? That we derive, or here we go, or as we move even further away, e.g. at r divided, let's see here, x divided by r that's equal to 10, then the circular, the disk, behaves like a point charge. Okay, so here we go. The point charge is right here. Anywhere else in between, you use this result here. That's the exact result. Okay, so we can put like that. Anywhere else, you are better off using the exact solution. that we got. This one right in here. Okay. And although, okay, the solution for x over r less than 0.1 is very convenient to use, and it applies not just to disc-shaped charges, but also any planar surface like a square plate, a square, rectangular, triangular, etc. plate. Okay? So keep this solution. So keep this solution, and on the top of that, this solution is very important here. Okay, we're gonna be using it over and over again throughout the semester. It's 6:43 right now. Let me see if we have anything else that I can tell you. Oh yeah, here you go. I can. Here is what we have. Here's the electric field distribution for the case in which x is very small compared to the dimensions of your charged plate. Okay, you have this type of electric field distribution. The electric field here is approximately equal to the electric field here is approximately equal to the electric field here. Okay? And that's for a plate that has a positive charge. The electric fields point away from the charge distribution. If the charge distribution is negative, the electric field is still uniform, but now it's going to point towards the charge distribution. Now, something interesting happens whenever you combine this plate with this plate here, one next to another. Okay, let's see, here you go. Suppose you put them close to each other. I'm gonna put another slide here. Here you go, so we can play a movie, okay? So let's say I decide to combine my positive plate with my negative plate. This one here is the x-axis. What's gonna be the net field when we put those two together? Don't forget, we are talking about an approximation in which the distance from the plates is much smaller than the size of the plate. Okay? Okay, we are going to have the fields of the positive plates are in blue, the fields of the negative plates are in red, right? Look what happens. Outside the two plates, the field of the positive and negative plates tend to cancel each other. To the left and to the right, and here to the right and to the left. See that? And they reinforce each other on the volume inside. Look what happens. We get an electric field 0, right? On the outside, and an electric field non-zero on the inside. Can you remember that? Okay? This is a very, and by the way, this approximation that you see here is very good. It applies not just for distances that are only 10% from the charge. It applies to even larger distances, okay? It's so good that, but you have to constrain yourself to the axis of this guy, because when you start to go outside, you see that effect that you saw in the lab last time. You start to see what we call a edge effect. 646. We're going to talk more about that. Okay? Remember this theoretical result, okay? What we're going to do next time, we are going to study what happens to a point charge subjected to a uniform electric field. A uniform electric field that's produced by planar charged a planar charge distribution. Okay, in this specific case, the charge has positive charge. This charge here is a positive charge subjected to an electric field. Is going to be accelerated from the right to the left. There are devices that work just like that. Okay, so the charge is going to move. Is going to accelerate from the right to the left. Okay, and that's going to be. And then we are going to also look at this problem here in which the charge, the positive charge, is going to come into the field from the outside. It's going to behave like a projectile. Once it enters the field, there's no electric field here inside. Okay, remember the weight doesn't is negligible. Okay, when the charge enters the field, it's going to be subjected to a uniform force, and it's going to describe a parabolic motion. Okay, just like a projectile does. Let's go upstairs. 6:48 right now. Okay, and we're not gonna do an experiment today. I'm just gonna walk you through what you're supposed to do for the experiment. Okay, and you're gonna plot some graphs. Okay, I'm gonna tell you things that I didn't tell you before during the experiment.